Hey students that will solve this problem here. Uh, they say that with nose above the water, about 95% of the body is submerged. So we must calculate the power that was expended, by a 70 kilogram woman treading water in this position. They say assume the average density of the human body is about the same as water. That means it's approximately 1 gram per cubic centimeter, and that the area A of the limbs acting on the water is about 500 centimeters square. So when we want to find the power that is expended, into the water by a person just to stay afloat, the formula to find this power is 1 over 2 the square root of the weight of the person times 1 minus uh, the fraction of the body under the water, F, times the density of the water over the density of the body, all these to the power of 3, and over the area of the limbs times the density of the water. All this is on the right. So this is the formula that we're going to use if we want to calculate, the power that is expended to stay afloat. So what we know here, we know the mass of the person that is 70 kilograms. So with the mass, we can calculate the weight, that is mass times gravity. I'm going to use as gravity 10 meters per square second to make it easier. So it would be 70 kilograms times 10 meters per square second. It would be 700 newtons. What else we know? We know that the fraction of the body under the water F is equal to 0.95 because they say that 95% is submerged. We also know the density of the body is equal to the density of the water, and all this is equal to 1 gram per cubic centimeters. That is going to be the same as 1,000 kilograms per cubic meter. I am converting always, the density that is given in grams per cubic centimeters into kilograms per cubic meter to have units, that are current. And we have also the area of the limbs, right? And they say that is 500 centimeters square, sorry. Let me erase this. 100 centimeters square. If you convert these centimeters square to meters square, remember that each meter square have 10 to the 4 centimeters square, or in 1 centimeter square we have 10 to the negative 4 meters square. So basically, to convert the centimeters square into meters square, we divide by 10,000. So we get 0.0500 meters square, and that would be the area of the limbs. So once you identify your data, you know you are ready to work with the formula a little bit. But look at this. We know that the density of the body and the density of the water are equal. This was given as part of the problem. So we're going to simplify our formula a little bit. So we can say that this is the square root of the weight times 1 minus F. Why? Because W, density of the water, rho W over rho, is equal to 1, right? So this quotient over here is equal to 1 because the density of the water is given, and the density of the body we said that it is equal to the density of the water. So this is 1. So now we are reducing the formula here to 1 minus the fraction of the water. All this to the power of 3 over the area times the density of the water. If we substitute, we have over 700 newtons, that is the weight, times 1 minus 0.95, all these to the power of 3, all over the area that we said there is 0.0500 meters square times the density that is 1,000 kilograms per cubic meter. If we are working, with kilograms, with newtons, with meters, or square meters or cubic meters, the power, the unit of the power would be in watts, or joule per second. So if we just do the calculation here, uh, just working with the numerator, we're going to have here 42,875 Newton to the third over 50 kilograms over meter. I was simplifying here this meter square with two of the meters we have here below. So when we have this Newton to the third, remember that Newton to the third would be kilogram to the third, meter to the third, over second to the sixth. Because what is a Newton? A Newton is a kilogram meter per square second. So we raise to the power of 3 of this becomes kilogram to the third, meter to the third, over second to the sixth. Now, if we divide that by kilogram over meter, this is the same that, say, kilogram to the third, meter to the third, over second to the sixth, times meter over kilogram. So this kilogram cancel with one of these kilograms, so now we have kilogram squared, meter to the third with this meter over here would be meter to the fourth, so this would be kilogram squared, right? Meter to the fourth, and then below we have second to the sixth. All this is under the radical, right? So if we now find the square root of this would be kilograms meter squared over second to the third. So this will be the same that kilogram meter over second squared times meter over second. Kilogram meters over second squared is Newton. Newton times meter is joule over second, and joule over second would be the watt. So this is why we get watts, right? As unit, as output unit here. So if we do the calculation that we have, we're going to find that the power that was expended is equal to 14.64 watts. So this was the power expended, to stay afloat by a person of 70 kilograms with 95% of its body, of her body, submerged in the water. So this is a really very interesting problem.